Anyway, here we are, and I want to thank you again for inviting me to come. I think it was 8 years since I was here last, so been a few changes in us all in that time. And this talk, I want to refresh this model of giant comets. The idea goes back to people like Clube and Napier, Hoyle and Wick-Ramersing, David Asher, Duncan Steele, and some contributions from myself and so on. So it's an idea that's been in the literature now for a good 20 or more, 30 years or more, and it's still an idea which is somewhat frowned upon by the mainstream in the subject, largely because of probably the implications of the hypothesis, and it's very difficult to prove because you're talking about things that may have happened thousands or tens of thousands of years ago, and it's not easy to find existing evidence for those sorts of phenomena. So what I'd like to do, recognizing that the present audience that probably, and anyone further afield, are not necessarily experts in astronomy and cometary astronomy in particular, I want to explain a little of the background about comets and large comets in particular, and then I want to talk about the standard picture for the origin of comets, namely this picture that the solar system, the planetary system I should say, is surrounded by a swarm of comets, a bit like a bee swarm, extending out at least halfway to the nearest star, the Oort cloud, and just briefly cover some of the evidence for that. And with that introduction, I then want to talk about a couple of recent results in the subject and focus in particular on the size distribution of the comets and the fact that there are large objects in the solar system which are known, and then explore the implications of the most recent giant comet, which we think may bear some relation to Encke's comet, the implications of that comet in the solar system as it might have been in years past, and some of the evidence or suggestions of evidence for supporting this general idea. So, without more ado, let me just show you some pictures of comets. And firstly, I want to begin with Donati's comet. This was discovered 1858, and it was visible for at least a couple of months. Easy naked eye object in the autumn of that year, and people said it was one of the most beautiful comets of the year, of all time. Well, I'm sure that wasn't quite true, but nevertheless, Hale-Bopp was the most recent giant comet that I remember seeing, and that was quite a long time ago now, so 1997. This is the Armagh Observatory, and this is a picture I took, and you can just, if you had maybe dark, I don't know if the lights could go out, but if they could, you might see the two tails of the comet. And what's quite amusing in this picture is the observatory's ghost. Can you see it? On the right-hand side, behind the shuttered windows. Now, you make of that what you will. Anyway, that's Armagh Observatory, which was founded in 1789. And I used to be the director of that observatory until 2016 or thereabouts. So another great comet, this one a comet of 1811, and it was visible for 260 days. That's one of the longest times that a comet has been visible, at least on record. And the point I'm trying to make is look at the size of the nucleus, estimated of course, around about 30 kilometers. Remember, Halley's comet had a diameter, an average diameter of about 10 kilometers. And then here's another comet which those of us of a certain age will remember, Hyakutake. While we were gearing up to see Hale-Bopp, this one came in, and it was an unremarkable comet except that it came very close to Earth. And again, we were very lucky because on the time when it came close to Earth, the skies happened to be clear. And because of the very close approach to Earth, this small comet, diameter about 4 kilometers for the nucleus, the tail extended right away across the sky. It was a very remarkable thing to see. The ghostly appearance of the long tail. I saw it, and I remember that very well. And some colleagues who were in really dark sites said they could see the tail extending over the whole sky. 90 degrees or more. So that was owing to the close approach. And it did have a kind of ghostly appearance. It was very interesting compared to the normal picture that you think of for a comet. And then there's famous comets, 1P Halley, number 1, the first periodic comet in the catalogue, and it returns every 75 or 76 years, basically every human lifetime. And everybody therefore gets a chance, if they're lucky enough, to see it. And it was the first one to be imaged by a spacecraft, and there's this iconic image of Halley's Comet, where showing in fact that this the surface was very dark, albedo of about 0.04 on average, with about 10 or 20% or so of the surface being active enough to eject gas, and with the outpouring of gas, the dust particles, which then, as they leave the nuclear region, the gas becomes the gas tail, highly structured, and the dust produces these rather diffuse and slightly curved dust tails. The gas tail, being blown out, if you like, by the solar wind at very high speed, owing to interactions with the solar wind, and the dust particles moving initially with the nucleus in the orbit of the comet, but then affected principally by radiation pressure, and therefore moving away in a slightly larger orbit than that of the comet. And since then there have been a number of spacecraft encounters with comets, and I just want to make a note that there seem to be a couple of characteristic shapes for these things. Maybe there's, if you had more, they'd fill in the gaps, but who knows. There's a kind of bipolar or dipole structure where you may imagine the thing as being a coalescence of maybe two proto-comets initially, or maybe more. And then there are more round ones, which may, I suppose, be the effect of originally larger bodies just having evolved it down in their sizes. But the point I really want to make is that all these comets which have been visited by spacecraft are relatively small, so average sizes of the order of 5 or so kilometers across. And that's simply because there are more small ones than big ones. When you look at historical observations of comets, you have to treat the drawings with a bit of a pinch of salt. But this one, by the comet of 1577, which was Tycho Brahe's comet, it was remarkable because it happened to pass close to the moon, you see in these two pictures. And around that time, people thought that comets were atmospheric phenomena, in other words, confined to the sublunary zone, where, according to the Aristotelian picture of the world, that was where things that changed had to be. And whereas at that time Tycho was able to observe the parallax of the moon, he was unable to observe the parallax of the comet, and therefore concluded that the comet had to be at least 4 times further away than the moon. And so that began to chip away at the prevailing Aristotelian dogma. And there were other things going on at that time. Tycho's supernova, 1572, Kepler's of 1604, and the first observations or the first recordings of stellar variables such as P Cygni or Mira Ceti, discovered in 1600 and 1596 respectively. And so again indicating that there are changes in the heavens, even though the Aristotelian picture tended to say there should not be. And once you start looking for things, then you see more such things, and gradually, it was not an overnight thing by any means, gradually the geocentric picture of the heavens was overthrown. And it did take a lot of time, as you're probably all aware. Then there are other pictures, again of the 1577 comet, that's the top one, and then 2 others, 1680, which was one of the comets that Halley was interested in, and Kepler too. At one point it was thought that there were actually 2 comets, but in fact it was the same comet has swung around the sun and has been seen, so it's a highly elliptical orbit. And then 1769, here's another comet that happened to be presented by Guillemin in his book The Heavens. And then I put this one up comet, the Great Comet of 1910. When people say they remember, not nowadays of course, they'd be too old, but when people used to say they remembered the Comet of Halley in 1910, possibly or probably they were remembering this one rather than Halley's comet. This was a Great Comet in 1910. So I put this up for that reason, and also because it's interesting to compare a drawing of the comet with a photograph of the same comet around the same time, and it's quite interesting to see the drawing picks out or highlights slightly different detail than the long exposure photographic image. So you have to be sort of bearing these things in mind when you look at the drawings, especially those from the distant past, that they will have been drawn highlighting particular things that the artist wanted to promote. And then there's a great sun-grazing comet of 1843. And the interesting thing about this one is it looked like a searchlight in the sky. Well, in that picture it does. And as an aside, I might mention the phenomenon, the auroral phenomenon, if that's the right word, of the phenomenon called Steve. Some of you may have heard of it. A number of years ago, not so many years, there were photographic observations of things looking like that and in the sky, and that reminded us in Armagh of observations, rare observations of comets which appeared to come and then disappear, and we looked into the history of it and then wrote a short paper about the historical observations of Steve, which turns out to be a phenomenon associated with the aurora, but not quite the same as the aurora. And I don't have time to go into it just now, but happy to talk about that phenomenon. It's still not thoroughly understood, but it's a very interesting phenomenon associated with solar activity and its interaction with the Earth's upper atmosphere. And then here's another one. And to get some idea of what people thought about comets in the 16th century and earlier, Paré writes, "This comet was so horrible, so frightful, and it produced such terror in the vulgar that some died of fear, others fell sick, and it appeared to be of excessive length and was the colour of blood. At the summit of it was seen the figure of a bent arm, holding its hand a great sword, as if about to strike. And at the end of the point there were 3 stars." And again, you have to remember, people thought this was in the atmosphere of the Earth, and therefore not very far away. On both sides of the comet were seen a great number of axes, knives, blood-coloured swords, among which were a great number of hideous human faces with beards and bristling hair. So, and I can understand that, having seen the comet Hyakutake, because remember I mentioned it had this ghostly appearance, and if you got a certain imagination, particularly if you thought it was not far away, it would be quite a scary phenomenon. And sadly, we've not seen such a bright comet in recent times, so it's very difficult to compare. And also, I suppose, light pollution and the transparency of the Earth's atmosphere has become much worse with industrialization and aerosols and dust in the atmosphere. So we don't get such a good view of comets as our ancestors had. So that's to give you an overview of what comets look like. And imagine a big comet, a much bigger one than the average. You would see all those stories, all those appearances writ large. And then what happens to comets? Well, they're believed to be dirty ice, snowball type objects in the nucleus. The nucleus sizes, as we mentioned, are typically a number of kilometers across, 5 to 10 typically, but there are larger ones, like I mentioned, diameters, a Hale-Bopp, the 1811 comet and so on, much bigger, 30 kilometers or more. And then, of course, there are even bigger ones, which I'll talk about shortly. And then as these comets come in from their source regions in the Oort cloud or wherever, outside the planetary system anyway, they break up due to a number of different and competing processes. Some comets are believed to be quite fragile, and you see nothing more fragile than this. It looks almost like a hand, imagine taking a handful of flour and throwing it it just breaks up, or a fluffy snowball, you know, dry snow, it just breaks up in the solar system. It's not as if there's much stuff there to break it up, but it just happens to be so fragile. And then another typical destruction mechanism is outgassing. In other words, every time the comet goes around the sun, there will be outgassing, loss of dust, loss of gas, and gradually the nucleus shrinks until it's not there any longer, unless it's kicked out by dynamical reasons. And then there are a category of comets which pass very close to the sun, called the sun grazers, and they are largely, not entirely, but largely the result of the breakup of a former giant comet. So they move in rather similar orbits, a family of Creutz's sun grazers. And there are a number of families of sun-grazing objects now known, which seem to have had a similar origin in the breakup of a larger parent body. And then there's another destruction mode, which is when a comet passes too close to a planet, principally Jupiter in this case. An example was Shoemaker-Levy 9, which was discovered in 1993 as a very unusual object, string of pearls it was described as, and it was subsequently found that this object was not orbiting the Sun, like most objects did, but in fact was orbiting Jupiter. And it orbited Jupiter with a period of nearly exactly a year. So, sorry, 2 years, my mistake, approximately 2 years. And on the prior peri-Jove, it had passed within the Roche limit of Jupiter. And at that point, what I mean by the Roche limit is when it passes so close to Jupiter that the tidal stresses across the size of the nucleus are such they're greater than the gravity or whatever else is holding it together. So they break the nucleus apart and causes the original progenitor to split up into a number of fragments, 20 or so. And these are fragments tens to hundreds of meters across, maybe as big as half a kilometer or more. And then subsequently, owing to what we would call secular evolution of the orbit, in other words, the orbit is coming around Jupiter, but every time it's getting closer to Jupiter. So this thing was going in an orbit that was destined to collide with Jupiter. In 1992 it got broken up. In 1994 all the fragments ran into Jupiter. It's tough for the Jovians. So had you asked an astronomer in 1991 what's the chance of getting 20 cometary impacts in the space of a week on Jupiter, the answer would have been very, very small. But in this case, the object was in a Jupiter colliding trajectory and it broke up. So all those fragments did collide and they were observed to collide and they left impact scars that were visible from Earth and the size, roughly the size of the Earth. And when you're interested, for example, as we were at the time, with the impact hazard story, it's quite interesting to note that these fragments, say half a kilometer, produced opaque dust clouds in the atmosphere of Jupiter, which isn't that different in its scale, height and so on from the Earth's atmosphere. I know the composition is different, but produced these clouds in Jupiter which were lasted for months. And so small objects of a few hundred, maybe 500 meters across, rather than canonical kilometer size, would produce a very distinct cooling of the Earth were one to hit the Earth, by analogy with Shoemaker-Levy 9. So that's an introduction to comets. Where do they come from? Well, the standard picture, and there's no reason really to doubt that this is the case in its essence. People work on the different aspects of this, of course, to try to prove more of it and find more details. But basically the picture is the galaxy is full of gas and dust clouds, and one of these slowly rotating clouds of hydrogen gas and dust begins to collapse, pancakes. Maybe it collapses as a result of the gravity and compression wave of the spiral arm density wave, or it's due to a supernova compressing it, causing it to go over the threshold for collapse, or whatever. Anyway, it pancakes and forms a disk. And then in a disk, it doesn't rotate like a gramophone record. The inner parts rotate faster than the outer parts, so there's a friction. And that's what's called viscous friction, and that causes the material to generally flow inwards, whereas some parts of the disk move outwards, and they carry away the angular momentum. So you end up making in the center a protostar, or rather I should say a massive object, which turns into the sun, proto-sun, and then collisions in the dust part in the disk, which is another complicated process which is poorly understood, but those dust grains gradually stick, a bit like hailstones in a thundercloud. They grow bigger and bigger, and ultimately result in what is believed to be the kilometer-sized planetesimals, which then produce the comets and the asteroids and the planets themselves, which dominate their respective planetary zones: Mercury, Venus, Earth, Mars, and Jupiter and Saturn and so on. And it's complicated because by then the whole structure of the solar system is difficult to predict because of the process called planetary migration, which is due to interactions, sorry, I've gone the wrong way, interactions between the objects in the planetary system as they are growing and with the larger gravitating disk. So the comets, which are ejected from that inner parts of the solar system, and by that I mean the planetary system region, ejected out beyond the region of Pluto into the Edgeworth-Kuiper belt and beyond, and then into the Oort cloud, another source region for comets. A good picture of the Oort cloud, although on a funny exponential scale, 10 AU, 100,000, 10 to the fourth. So don't imagine it's got a shell-like structure. The structure is more and more numbers per unit volume of comets as you approach the inner solar system, except when you get towards the planetary system, where the planets have basically swept out a hole in the middle. And there are a couple of things on the right-hand side from our book, The Origin of Comets, and you'll see a picture where we've just got the planetary system and rings of objects, a planetary system with an extended disk of objects, and a planetary system with a model which is more like a spherical or spheroidal cloud of comets surrounding it with a hole in the middle. And you can see that most people explore this picture, but it doesn't mean to say that there are not objects in rings between the planets, and there are not objects in higher inclination orbits, but still within the more compact central parts of the solar system, extending out to a few hundred or maybe 1,000 AU. And then you go beyond that, you've got flattened disk, you've got a flared disk leading into the Oort cloud, which is more like the standard picture, and you may imagine a more spherical system if you had a different theory for the origin of comets. Maybe they formed during the collapse, during the original pancaking of the solar system, and so you end up with a more spherical cloud of comets around the solar system. Who knows? But still, the end result is that you have to explain what is observed, and it may be more difficult in such models than the conventional picture. And then there was the evidence for the Oort cloud, because these objects are far too far away to see, and so what is the evidence, you might say? Well, I was going to say 50 years, it's actually nearly 70 years, more than 70 now, years ago when Oort was working on this. He looked at what were called the original 1/A value. A is the semi-major axis of the ellipse, in effect half the length, if that's an elliptical orbit, half the length. And the 1/A is plotted partly for convenience, but also because it reflects the energy, the binding energy of the orbit. So the 1/A is a useful thing. And in 1950, it was just possible for people to calculate, clever people, not me, but clever people to calculate the original orbits of these comets coming in. In other words, before they were disturbed by the influence of the planets, namely Jupiter and Saturn principally. And And at that time in 1950, he had only 19 with accurate, quote, original orbits, and with small mean errors. And that enabled fine-grained binning of the distribution for the first time. And he showed that most of the objects fell close to the parabolic limit, with semi-major axes bigger than 10,000 astronomical units, in other words, coming from at least 20,000 AU. And none were much more tightly bound than falling at that part of the diagram. And the point really he made was, note the extreme narrowness of this peak compared with what Jupiter does to them after they go through the planetary system on average. So this lot comes in like a kind of a delta function, and they go out with a wide range of energies, some to be ejected, others to come round again, but with energies spread out along this part of the diagram. And when you compare it with more recent data, this data from 2008, the situation is precisely the same. When you plot the same, or three or whatever it was, I forget how many objects. I thought it was about 200 or 300. Oh, here we are, 200 of the best orbits. And you can see on the left-hand side. But when you blow up this spike, you can see again this very fine-grained structure where everything basically concentrates close to the parabolic limit. So that story is the essential observation to explain. And in modern terms, the argument goes as follows. We see one, quote, new, dynamically new comet, and in these terms I define it to be within Jupiter's orbit in perihelion distance, and brighter than absolute magnitude 7, in other words, diameter about 5 kilometers or so, and semi-major axis bigger than 20,000 AU, periods 3 to 30 million, and the point is 3 to 30 million years is very short compared to the age of the solar system. And the other point to make is that none of them go back to where they came from, because either they're ejected totally or they come back again, ultimately to be either ejected or to disintegrate owing to outgassing or collision or whatever. And so the point is that all these comets with Q less than about 15 AU are lost within a timescale much less than the age of the solar system. So either the cometary phenomenon that we see is a transient phenomenon, or there's a long-lived reservoir to replace those that are left. And Oort adopted the reservoir hypothesis, the primordial, quote, steady-state solar system hypothesis for the origin of comets. And I won't go into the details too much in this talk, but the real point is that the new comets are only lost if Q is small, and therefore the reservoir must contain long-period, large Q orbits. And then you can see how if you've got a cometary orbit which is very long period, very highly eccentric, and then a passing star goes by, then the passing star gives the comet a nudge at aphelion, where it spends most of the time. And that because of the lever effect, that changes the angular momentum and therefore changes Q by a large amount. And you can compute models of the Oort cloud with it being gardened, not just by stars, as Oort had, but also by molecular clouds and the effects of the overall disk of the galaxy, the so-called galactic tide. And this picture of M13 shows the general picture as I tried to explain with this stick. There's the cometary orbit, there's a passing star. Out there it's nudged a small amount relative to the Sun, and therefore the orbit is changed relative to the Sun, and the external perturbations are continually shuffling the orbits of the Oort cloud around. So the standard view, comets are primordial solar system objects. They're formed by a coagulation of dust, which is originally interstellar, but ultimately protoplanetary dust from the system, so there's a hierarchical growth. Coagulation proceeds rapidly where the orbits are shorter period and more slowly farther out, and that general idea goes all the way back to the mid-18th century and ultimately produces protoplanetary building blocks cometesimals and planetesimals. And then a whole lot of detail stuff. How do you make planets out of stuff colliding in the inner solar system? What happens to the orbits of the biggest ones, Jupiter, Saturn, and so on, under planetary migration? And then the late stages of this process, the bombardment of those planetary and satellite surfaces that have already been formed, like the Moon and Mars and Mercury and so on. And most work on the origin of comets now focuses on simulations of the origin and evolution of the solar system and the formation of the Oort cloud, the structure and evolution of what we call the trans-Neptunian region, which is the region beyond Neptune in the inner solar system, out to perhaps 200 or 300 astronomical units, and the Edgeworth-Kuiper belt and beyond, and then the dynamical evolution of short-period comets, both of the Halley variety and the Jupiter family types, and more recently the origin of giant comets and centaurs in the Jupiter to Neptune region and beyond. And the point about those are the large number of discoveries. Sometimes these are called scattered disk objects because they're thought to have been scattered by the planets in their formation. But they're in the region of Jupiter to Neptune and beyond, and large numbers are being found with every week that passes. So let me now briefly talk about the recent discoveries that I want to highlight. I want to talk about two things on this slide: sun-grazing comets and comet trails. And my first point is sun-grazing is a common cometary end state, much more common than anyone thought 30 years ago, shall we say. And they frequently fragment, comets that is. Every month, I mentioned the Creutzfeldt family, but every month spacecraft orbiting the Sun have detected of the order of 10 small pygmy comets. In other words, comets with diameters with nuclei in the range 10 to 100 meters, the sort of size object that ran into the Earth in 1908 with the Tunguska explosion, run into the Sun. So every few days one does it. And that illustrates a very common phenomenon, namely the enhanced collision frequency of objects owing to the particular geometry of the orbit. So here you have a stream of comets, fragments of comets, of a comet, arising from the breakup of the main particle. And then, because of that orbit, they're a bit like SL9, Shoemaker-Levy 9, a bit like that, the other fragments are destined to collide. And so you get an enhanced collision frequency. And the main sun-grazing groups is the Creutzfeldt family, 1843 I mentioned before. The D1 indicates it's disintegrated or collided with the Sun, and countless smaller objects. And there are more than a dozen smaller and distinct sun-grazing families. And long-term planetary perturbations cause many objects to become sun-grazing. And here are three examples: Halley, Machholz, and Encke. Okay, so that's one point. And then the second point, the dust and sometimes the larger bodies ejected by comets or fragments of comets initially form dense, narrow, co-orbiting trails. In other words, the meteor stream, before it spreads out, can be quite narrow. And these trails can sometimes survive for hundreds of years, given the right circumstance. So you've got the Leonid dust trails, for example. The Leonids happen every 33 years. Every time the comet comes round. Every year you see Leonids, but there's a spike in the number of meteors per hour every 33 years, roughly. And in this case, the most recent one was 1998. We were predicting a burst of meteors, but then there were large bodies unexpectedly observed about 10 or 12 hours before the main shower. And it turned out that they were produced by objects ejected from the comet in 1333. And they hadn't spread out, as you would expect them to do, around the orbit since then, owing to what's called a resonance. So that means they spread out a wee bit, and then they converge again. Then they stretch out, and they converge again. So they're kind of focused, concentrated in a particular parts or several parts of the orbit. It's a picture of pygmy sungrazers. I forget when this was, probably says on that picture, but can't read it. But you see two of them. Here they are, going in and basically running close or into the sun. The middle bit, of course, is the occulting disk, so you can actually see anything. And this to illustrate the sun-grazing end state of a typical Halley-type comet. You can't do better than choose Halley itself. And this is an example of that. And here, this plot, the perihelion distance, goes from 0 to plus a million and 0 to minus a million years. And basically what you see is a secular evolution of the perihelion up to the present day, and then falls into the sun, about there. And there are other elements of the orbit, inclination, eccentricity, and semi-major axis. And the point really, rather than a random walk, the comet is always tending to move in one or another mean motion resonance with Jupiter. And here's another example, or two examples. The Kozai cycles, they're called. And the top part of this diagram shows the semi-major axis, very, very flat, unchanging for Machholtz, over plus or minus 10,000 years or so. Whereas the perihelion distance is oscillating between 1 AU roughly and 1/10 of an AU. And that's the characteristic of the Kozai cycle. It produces large changes in eccentricity and inclination and leads to the sun-grazing phenomenon, as well as, in the case of Shoemaker-Levy 9, Jupiter grazing phenomenon. And is such a powerful dynamical effect that it basically occurs everywhere you've got axisymmetric gravitational fields. In this case, what's the axisymmetric field? This is the pericenter of the Shoemaker-Levy 9 object before it ran into the Earth, into Jupiter there. And in that case, you've got Jupiter with the comet going around it, and Jupiter's going around the sun. So if you're in the Jupiter frame and the comet's going around you, the sun is going around every 11 and something years, and it gives you an axisymmetric, on average, an axisymmetric potential field, and it's that which is affecting the Shoemaker-Levy 9 comet and causing this. So even in that case where you think it wouldn't be very axisymmetric, on the average it still has the same effect. And you see the same dynamical phenomenon in any such structure, whether it's binary stars, planetary pairs, Oort cloud. That's a bit like the galactic tide and the disk of the galaxy, exoplanets, multiple star systems, and galaxy satellites, a very general phenomenon. And this happens, in fact, also to the comet Encke. So here is an example of Encke's orbit going forward for 80,000 years, an example, and you see the semi-major axis hardly changes from 2.21 to 2.24 or so AU, but in all that time, the perihelion is drifting down in a systematic way, a secular way, with these superposed oscillations. And the inclination is drifting up, but with these oscillations. So that's the Kozai oscillations superposed with some background secular effect that drives that comet in towards the sun within a modest timescale, 80,000 years or so. And now if I just look back at the meteor trails, the Leonids, observations of this shower go back to 899 at least. It's a reliable shower. You see it around mid-November. But every 33 years, as I said, you see outbursts in the intensity of the display, and sometimes exceptional meteor storms. And in 1834, Olmsted and Twining were the first to infer from the observations that they collated that there was a causal connection between comets and meteors. And this was only a generation or so after the first suggestion that comets or even meteorites were extraterrestrial objects from the solar system. And yet it was a further generation before that link between comets and meteors was further firmly established with Comet Tempel-Tuttle. And this picture from David Asher shows very nicely what goes on. He was one of the several authors who first were able to compute the likelihood of the Earth passing through a dense cometary tail. And you have to imagine a kind of a large drainage pipe being the meteor stream, very large, and imagine fiber optic tubes within it, very fine stuff in it. And so when the Earth goes through the drainage channel, there's a period of days, up to a week or more maybe, when you see meteors. But if you happen to hit one of those fine ones, you'll see a large surge in the number per hour. And you can actually relate each of these fine-grained structures to the time of the comet's previous perihelion, when those dust particles were ejected. And in the case of the 1999 event, here's the Earth going round its orbit, 17th, 18th and 19th of November, and it passes close to the 1899 trail. In year 2000, it misses them all, basically. Year 2001 passes close to these two, 1767, 1699. Year 2002, straight through the middle of 1767 and 1866. So for the first time, people were able now to compute the likelihood of getting intense meteor storms from comets. And you have to thank David and his colleagues for doing that. And now the last thing I want to remark upon, I'm not quite finished yet, I'm afraid, but is the question of the giant comets. And they exist both in the long period flux, in the Halley-type comet, short period comets, and, as I'll come to, in the Jupiter family. So the point really is that with the flux of comets, the number per unit distance from the Sun is nearly uniform, and the number versus diameters, the cumulative number, decreases only very slightly, roughly proportional to inverse diameter squared, up to some point where there's a turnover, but up to at least about 50 kilometers. And you can imagine these comets are quite rare, and so it's very hard to find exactly where that turnover occurs. But up to 50 kilometers, remember we've seen comets with nuclear diameters estimated to be at least 30, and I remember there's a comet, not a short period comet, called Schwarzmann 1, which I think has a nucleus of diameter 60 kilometers. So you have to bear in mind that these are observational results in many cases, albeit with uncertainty. And so you can work out how often this happens. How often does one big one, a giant, being anything with diameter bigger than 50 or 100 kilometers. So 100 kilometers is 10 times bigger than Halley's comet and 1,000 times the mass. And so one of these should come into Jupiter's orbit every 10 to 50,000 years. And similarly, when you look at the Halley types, giants with these sizes enter the Halley-type population again roughly every 10 to 50,000 years. It doesn't really matter too much if it was 20 to 100,000 years. It's still short timescale compared to timescales of the solar system. So it is something which happens frequently in terms of Earth history, and perhaps even in terms of human history. And now we look about the centaurs. Remember, the centaurs are objects with perihelion distances between Jupiter and Neptune. The definition that people use varies, but I tend to assume that anything with a perihelion distance in that range can be counted as a dynamically evolving object and call it a centaur. Some authors, some authorities prefer to constrain the definition to be only objects that orbit entirely within the planetary system. But that's an arbitrary division to me. The objects are really comets coming in from outside the planetary system, and if you integrate their orbits, sometimes they'll go out beyond the planetary system, sometimes they'll move in. Okay, so these are large comets. All centers are large comets, even though they may not show outgassing because of their distance from the Sun. The semi-major axes range from within the planetary system, as I mentioned, up to 1,000 AU or more, when I suppose most people would call them Oort cloud or inner Oort cloud objects. And as far as one can tell, these two have a flat size distribution, a cumulative distribution varying as inverse square of diameter. And the first one to be discovered, which we wrote a paper on in 1977, has a diameter of 220 kilometers. And the half-life for this one is moving beyond Saturn at the moment, is to become a Jupiter family comet, is around about 100 to 200,000 years. And its dynamical lifetime before it gets booted out is around about 1 million years, maybe 2 or so, a few million years, say. And so Charon, during its long evolution of a few million years, has the opportunity to come into the inner solar system, out again, in again, and out again, so many times, so that it has a chance at least 5 or 10 times on average to enter the solar system as a short period comet. And this is an object with diameter 200 kilometers. So it's 10,000 times the mass of Halley's Comet. And it could become a short period comet. Probably, I would argue, has been a short period comet. We'd be relatively unlikely to see it on its first approach before it's yet come in at all. And there are now about 1,000 centaurs known in the solar system, and many more large objects discovered moving in orbits beyond Neptune. Many centaurs have diameters bigger than 100, Charon being one example, and they have dynamical lifetimes ranging from 1 to 100 million years, depending on which planet is the dominant one controlling their evolution, whether it's Jupiter or Saturn, Uranus or Neptune. And again, they are thought to be an important, if not the dominant source of Jupiter family comets. And so giant comets are coming into the solar system every 20 to 50,000 years, maybe every 100,000 years. But it's a short timescale compared with other timescales of interest to people. And here's an example of a typical Chiron-like clone, and it's just an illustration of what can happen. So going backwards in time from the existing object, a variety of objects are calculated, not one of them being true to the real object probably. But this is an example where the perihelion distance goes back, and there's the Earth's orbit about there. So it drops down to 2 AU and then down to 0.5 and less for about 5,000 years, and then it gets booted out again to beyond Jupiter. And so there's a typical example of such an object's evolution. Here's another phase, just looking at the perihelion distance, integration by Bill Napier in this case, and it runs down through Earth crossing. This is now integrating forwards through Earth crossing, Venus crossing, and out again, and therefore close to the Sun all that time, producing an awful lot of gas and dust in the inner solar system, which would have a very significant impact on our planet. So the points I want to highlight at this stage is that giant comets larger than 50 or 100 kilometers exist, and they enter Halley type and Jupiter family short period systems at mean time intervals of the order of 10 to 50 or perhaps 100,000 years. Now, comets, even ordinary ones, can often become the most prominent objects in the sky, and their study and their observation goes back thousands of years. Comets also touch on many areas of astronomy, not least solar system science, but also origins of life and so on. and they've had a significant impact both on the Earth over the eons and on the development of scientific ideas. And the key thing to remember is that in the last 30 or 40 years, Earth is now becoming recognized as an open system in touch with its near celestial environment, whereas previously people were much more content to think of the Earth as a isolated object under a fixed light, the sun, just sitting there, well, maybe going round the sun, but the complexity of the Earth system was sufficient. Don't bother me with anything more complicated like things coming from outside. But now we realize that things coming from outside and changes in the sun, for example, are important. And so, to me, this is a paradigm shift which is as significant as moving the Earth from the center of the solar system to the Copernican revolution. The solar system is a very leaky system too, because as I mentioned, during their evolution, long period comets, a lot of them are booted out. So the interstellar medium in the galaxy is very full of cometary stuff, whether it's small bodies, dust, large dust particles, which you don't detect very easily, or fragments of comets, kilometre-sized objects. And then there are questions, so molecular clouds and the wider interstellar medium must be full of these debris, not just from the Earth's solar system, but also other planetary systems. And what about comet clouds around other stars? And then you can discuss orphan or interstellar comets, which were formed or thrown out at a very early stage in the formation of a planetary system. So there's now becoming a new emerging worldview about comets, if I can put it that way. It's a balance between what was previously regarded as a catastrophist picture and the subsequent uniformitarian view, namely that comets are destroyers of life when they run into the Earth, for example, but they also can bring to the Earth the necessities of life, the water, the organics. And people talk about what brought the water comprising the Earth's oceans, and they often talk about water-bearing asteroids or comets. So it's an interesting merger between previous ideas. And now in the last part of the talk, I want to talk about the most recent giant comet, which is Comet Encke. And this is, or a fragment of the giant comet. Comet Encke and the Taurid meteor stream. As I mentioned, this work goes back to Klube and Napier, and Steele and Asher, and people like me have made relatively small contributions to the story, but the picture is fairly well established, even though it's not widely accepted in the main body of opinion. But if you look at the story here, 2P Encke is an unusual short period comet in terms of its brightness. It's not big, or it's not a bright comet, but it's now recognized as playing a key role. The nuclear diameter is typical of those small ones I showed, about 5 kilometers. And yet the orbital period is the shortest orbital period known. So it's in a very unusual orbit. With a period of 3 1/3 years, it comes round 3 times every decade, and because its aphelion never quite reaches Jupiter's orbit, it's a very stable orbit. It's affected only by these Kozai resonances, which are caused by the axis symmetry of the Sun-Jupiter system. And it seems that the orbit is stable for tens of thousands of years, though as I showed, it eventually falls into the Sun. There's a meteor stream attached to this comet, or associated with it, called the Taurid complex. And from the width of the stream and its various components, it's recognized that that complex is tens of thousands of years old. So it could be 10,000 or 20,000 years more likely old. And that leads one to think that this Encke's comet is either a fragment of a larger progenitor or the remains of the larger progenitor comet. And there are 4 principal parts to the Taurid complex, quite apart from the asteroids that are thought to be members of it. The northern and southern Taurids, which are visible at night in October through November, and the daytime beta Taurids and zeta Perseids, through which Earth passes in through May and early July each year. and the Tunguska event coincidentally associated with it, probably part of the Beta Taurids, though of course some people dispute that. I mentioned that picture before, showing the stability of the orbit for tens of thousands of years, and yet with these oscillations drops into the Sun in the future. And this shows the orbit of the four components of the Taurid complex. So you see they're all different. They're quite different, in fact. And it's that variation which leads one to believe that the complex is very ancient, because otherwise how could the orbits be so diverse and yet connected? So, and here I've mentioned the first point of Aries lying to the right. So there's the Sun, first point of Aries in that direction. The first point of Aries is the direction of the Sun as seen from the Earth at the spring equinox. So if you're around on March the 20th and you look at the Sun, then you're staring in the direction of the first point of Aries. So just give you a direction, because it sort of tells you that that's March, so that's June, that's December, that's whatever is, sorry, that's June, that's comes after June, September, and there you have December. So in this case, the Earth in its orbit, March, June, September, October, November. That's when it's crossing the Earth's orbit. Daytime Beta Taurids cross in June. The southern Taurids, the ascending node, crosses in October or November, and so on, just to give you an idea of the seasons. And the other thing that's remarkable about Enki is not only does it have a kind of a fuzzy coma and not much of a tail, but it does have a trail. In other words, in the orbit are dust particles which are associated with the comet in a dense trail rather than a tail. And then there are speculations, perhaps more than speculations, that just like with the Leonids, there can be a resonant swarm associated with the comet in its orbit. So this swarm of particles moves with the comet every 3.3 years around the Sun, as well as the main meteor stream associated with the orbit. But as far as I recall, there was no actual detection of this stream the last time people looked. But it may have been that it wasn't, there were things working against the observers on that occasion. But that's kind of a prediction waiting to be confirmed or ruled out. And then there's another very interesting result. NASA's Messenger spacecraft, which orbited from Mercury for 4 years, up to 2015, it detected calcium, amongst other stuff, ejected from Mercury's cratered surface. And the explanation for that, it was said, is that meteoroids running into Mercury were sputtering the surface, cratering it if you like, and ejecting stuff off the surface of Mercury. And the spacecraft orbiting Mercury detected that at certain times in the Mercury year. And Tolis Christou, who works at Armagh, as well as two colleagues in the States, they published a very interesting piece of work in 2015 showing that the observed meteoroid impacts, yes, they were associated with the Taurid meteor stream, but when you look at them in detail, in order for the particles now to be hitting Mercury and being detected now by the spacecraft, those particles had to have had orbits that were like Enki's comet 20,000 years ago. So this is like a smoking gun telling you that Comet Enki or its progenitor must have made thousands of revolutions around the Sun, and therefore must have been a bigger, brighter comet in the past than it is now. And so the assumption is that our ancestors must have witnessed this comet. Maybe it was 50 kilometers across, maybe it's 30, but it was much bigger than it is now, and it comes close to Earth from time to time. And therefore they would have witnessed its associated effects, fireballs, meteor storms, and impacts like Tunguska, as the Earth periodically encountered the debris streams. So there's a picture here just showing, taken from NASA, J. Friedlander, who published this image, showing the Sun, Mercury going around the Sun, and the Taurid meteor complex running into Mercury at that point in its orbit. So you get the general idea that Mercury, just like the Earth, is a bombarded planet, and these impacts of these particles were ejected tens of thousands of years ago. Well, maybe not several tens, but 10 to 20,000 years ago from an orbit like Encke. And let me just illustrate now in the next number of slides. I'll flick through them very quickly. This is the orbit of Encke now, in the year 2000, and I'll go back in time, and you'll see how the orbit precesses with time. And the first point of Aries, as before, is to the right. And so that's March the 20th, and that's June the 21st, that's September the 21st, and there's December the 21st. Give you an idea of the seasons. And when the node, as it is, it's above the Earth's orbit here, so we're not in danger from that trail just now. But when the node is crossing the orbit of the Earth, then you expect fireworks. So you can see the direction of the first point of Aries in this one at 1800, and I'll just flick through it. I'll do it a couple of times. So you can see how the orbit shifts in time, and around about 300 AD is the first node crossing. And there it is again around about 0 AD, and then it's not node crossing again for quite a long time until around about 2500 BC and 2700 BC. Now, it's very difficult to be certain of those dates because they're all variational orbits. You could produce other orbits that gave you different answers, but the pattern is the same. So if I want to if I go back, moving forward in time, you can see how the orbit precesses, and you can see how the nodes occur in pairs, separated by a few hundred years, and that's the signature of this Encke comet event, which is quite interesting. And the Taurid complex, so here they are, just to blow up of the previous diagram of the orbit, the meteors. So note that the meteors are node crossing, but not Encke's comet. So you only see meteors when they hit the Earth, of course. So they have to be node crossing. And the southern Taurids, the daytime Beta Taurids in June, and the daytime Zeta Persids, around about the same time, end of May. So, so here's another diagram. This is from Steele and Asher, paper in 1996. They computed variational orbits based on Encke's comet, nominal, and then plus or minus a bit. And they found that the rate of precession depends on the comet's orbit, and that's not known accurately for more than a few hundred years. There's no real constraints. Though the paper by Christou gives you some constraints which you could possibly apply. And when Encke is node crossing, you expect the Earth to be running through the densest parts of the trail containing the biggest fragments of the comet, maybe Tunguska-sized objects, or more of them. And you get meteor storms and episodes of bombardment. And what happens, going back in time from the year 2000 to 0, minus 2000, to 4000, minus 4000 BC. So you're going back, you get a nighttime shower and then a daytime one, nighttime and a daytime. And that's the pattern going backwards in time. It's about as far as it's worth doing it. And so the prediction is you get a bombardment period lasting perhaps a century, within which there's heightened activity every perhaps 10 or 33 years because of the orbital period of Encke, a bit like the Leonids. And therefore, these are the implications which I want to talk about briefly, and then I'll go on to speculate about other stuff, and then that'll be the end. So, giant comets exist, no question of that. The only question is how many are there? And if there are as many as there seem to be, then they enter the solar system at least as often as every 1 per 100,000 years. And so it's not unreasonable that there should have been the effects of one in the last 10,000 years, producing a huge increase in the number of boulders, meteoroids and dust in the interplanetary complex. And unless the comet is very stable, most giant comets will not last that long. They'd be booted out just like ordinary Jupiter family comets, though they will of course have bigger effects in terms of outgassing and stuff. But for some reason, the Proto-Enki got into a very stable orbit and therefore was able to undergo hierarchical fragmentation, a bit like the Croûte's progenitor around the Sun, a bit like that, for at least the last 10 or 20,000 years. And so the expectation is there would be a more time variable and much more active sky in proto-historic times, with pairs of bombardment episodes separated in this case by 300 years, occurring around about 300 BC to 400 AD, and then again sometime in the interval 1700 to 3700 BC. It's not very accurately known, but that's the general picture. And for those of you who are like Velikovsky, this picture puts an astronomical framework around the other musings of Velikovsky. And then node crossings occur 20 to 22 days earlier for each millennium, allowing both the precession, as we've seen, and the precession of the equinoxes. That's consistent with the present mid-October nighttime shower happening close to the midsummer solstice around about 3500 BC. And so just to wrap up, I want to flick through a few implications. So the early Greek ideas, Anaximander's jets of fire, where did that idea come from? That the meteors or stars lay below the sun and moon. Comets as meteors and portents, and I won't dwell on that because you're all familiar with the idea that comets are associated with meteors and devastation and all the rest of it. Comets in literature and poetry. William Carleton, who is an Irish poet, author, he wrote lines to Halley's Comet, where he drew very much on that heritage of in the literature. and then comets presaging the death of kings. Plenty of examples in the literature of that. And I want to briefly mention that the earliest ideas that we can know about, going back to about 2000 BC, talked about comets as being earthly bodies akin to planets. But gradually, as time moved towards 400 or so BC, there was a trend towards them being increasingly imaginary objects. And then later, those imaginary objects eventually became almost invisible, and Aristotle's atmospheric picture of comets prevailed. So comets were not even extra solar system and extra Earth system bodies, but terrestrial bodies. And then, without going through all of that, I just want to briefly say that as comets up to the Age of Enlightenment appear unpredictably but move like planets, comets and meteoric phenomena were scrutinized as omens, but mankind's puzzling fear of comets was never properly explained. But the picture that we're giving you with Encke's comet explains how that could have developed in the period since 2,000 or 3,000 BC. And now, 2,000 years later, with the Earth now recognized as an open system, our atmospheric ideas of comets get replaced by a more correct celestial picture. And the modern ideas, the modern debates about comets bring together aspects of both the distant historical views. And principally, we now recognize comets as objects in the solar system that can bring destruction and change to the Earth, even on timescales of historical interest. So we're familiar with the Near Eastern view of civilization, we're familiar with the Mediterranean view, but if you look at megaliths, the Atlantic view, you can see what look to me like pictures of comets where you've got heads and tails and stuff, and you can interpret stone circles, and I'm not saying I have a proper explanation of this, except to say that quite often these look for all the world like meteors, fireballs or comets in the sky. Now I know there are over 100 explanations for cup and ring marks, so I'm not saying necessarily that this is true, I'm just pointing it out as a consistency story. Is a huge bay car on the Argyle Peninsula. Here's a megalithic stone with what looks to me like a comet inscribed on it. So perhaps people saw stuff in the sky. Here, Bakemore stone circles in Northern Ireland. So people were doing this stuff, and they were doing it for a reason, and one of the reasons may be that they were familiar with the fact that from time to time heaven came down to earth. The comets destroyed a village or an area around them, and they attributed the result to the gods. And perhaps I mentioned once before the story about Akbi, the ground zero of the Tunguska phenomenon, because Akbi is a totem pole erected by the scientists who visit the site without a thought as to this being possibly a mythology that's developing. They just erected it for fun, and there's now a mythology that you have to travel there and leave an axe or a bus ticket or a coin, something of value to yourself, to make sure you will once more go back there. And I visited it, travelled thousands of kilometres to deposit a bus ticket at Akbi's feet. And so you can see how these impact sites could potentially become sites of religious heritage as well. And so ancient societies are obsessed by the sky. Why is that? Possibly because the sky was more active in the past, and that Tunguska size events were much more common in the past. And then you have the possibility to explain problems like the Milky Way, Aristotle believing it to be in the sublunary zone, and most importantly, Metrodorus, and the Milky Way is the former path of the Sun. Anaximander, the Milky Way lies in the shadow of the Earth. Well, you don't need the Earth to rotate to explain that. All you have to say is the Milky Way, as it's described, is in fact the zodiacal light, which in those days was much brighter than it is now. So, two more, this slide and one last one. Comets can sometimes be the most prominent objects in the sky, and their study goes back thousands of years. They touch on many areas of astronomy, and Earth now is viewed as an open system in touch with its near-space environment. The solar system is very leaky, and therefore the interstellar medium contains large dust grains, cannonballs, boulders and comets in the interstellar medium. There's an emerging modern picture of comets, which is a balance between the historic catastrophist view and subsequent uniformitarian views. And giant comets run into the inner solar system at least as often as once per 100,000 years or so, and has played a major environmental and societal role. So you can begin to see how you're bringing together the uniformitarian views and the other catastrophist views. And I just want to leave this slide up, I think. I think that's probably my last slide with my acknowledgements. So the last slide just points out generally that there are three strands of interest that underpin humankind's interest in astronomy. There's the cosmological strand, which you may call the quasi-religious strand, which is basically the quest to understand our origins, Earth's place in the universe, the origin of religion. Why do we place gods in the sky? Where did the idea come from that Jupiter hurls thunderbolts? It's never done that in its whole life at the Earth, as far as one knows. The practical strand, of course, and this strand includes the subsequent one, which is the strand to understand Project Spaceguard, in other words, defend the Earth from the comets that may have destroyed the dinosaurs. And then there's the pure scientific inquiry, which some of us like to develop, but we're developing techniques, developing understanding, which all helps to understand the world we're in. So we've lived through a golden age, and there have been unprecedented advances in each of those areas of inquiries, and those three strands come together under the heading of giant comets. So it's very interesting to be living at this time when our understanding of solar system astronomy and giant comets has potentially so many impacts on other spheres of inquiry. So thank you very much. Happy to take questions if they've got time.
Any preferred direction from the Oort cloud? I mean, there's some controversy at one point. There's supposed to be some preferred directions that the comets are coming in from long-period comets, or are they random?
Yeah, I mean, some people. Basically, the story is they're more or less random, not quite random. Yeah. The Oort cloud isn't quite spherical. It's more like a flattened rugby ball. You put your foot on a rugby ball, you get a triaxial ellipsoid. So it gives you a general idea of the shape under the influence of the galactic potential. Yeah, some people have made not so much of comets, but as centaurs, I think, the direction of discovery. Well, maybe the direction of the orbits of some of those centaurs, indicating that there's something out there which is controlling the orientation of those orbits, but as opposed to the comets. Whenever people have looked hard for changes in the, well, for, how can I put it, directions in the sky where you see more comets coming from, long period comets I mean, in the end it's all down to fluctuations and statistics. Yeah. And it's one of those questions, if you had an answer, you could probably say, oh yes, the observations are consistent with it. But at the moment, they're consistent with comets coming in more or less randomly around the sky.
How close do you think another star would have to come to have an influence on the Oort cloud?
Well, it has an influence quite a distance, because the gravity, basically what's going on is that if the star doesn't penetrate the Oort cloud, it passes way by, then the comet is attracted to the star as the star goes by, and the sun is attracted to the star, but in a slightly different amount, and so there's a difference, and therefore the orbit of the comet relative to the sun is changed.
You're talking gravity again. You're talking gravity.
Yes, yes. And the other effect is when a star tunnels through the Oort cloud, and basically it drills a hole in it. So any comet that gets too close to the star is ejected. So you have a stars running through the Oort cloud much closer than the size of the present Oort cloud, and effectively the solar system is booting comets out throughout that tunnel. Yeah. So and if it had been that a star had come very close to the sun, let us say through the planet, within Jupiter's orbit, probably what would happen is the sun would have been booted out of the Oort cloud, and then you'd have an orphan Oort cloud floating around the galaxy, and the sun and the passing star would have been off somewhere else. And so presumably those Oort clouds in the interstellar medium must exist, because that must happen to some stellar systems. And the idea that most stars, 50%, maybe 30%, most stars have planetary systems, and by inference or assumption, most stars therefore have Oort clouds, and some of those systems will have had close star encounters, and which basically leave their Oort clouds of comets floating around to be dispersed by normal effects of stellar action. Yeah, but it is gravity. Yeah.
I think you said that the Tories were particularly bombarding 300 BC and 400 AD, or thereabouts.
Yes, that's right. Yes, that's the range. But the interval, depending on the orbits, the interval between the two is approximately 300 years. Now, it could change if you change the orbit, or find a means of, because to me, 0 and 300 BC, or 0 and 300 AD, isn't a terribly interesting time. I'd much rather it be 450 AD and 0 or something like that.
Any sort of record of people seeing this?
Don't know. I mean, I suppose I'd point to things like end of times and people. It's very difficult to separate observations of fireballs from observations of unusual and bright aurora. So you can sometimes get these things confused in the literature, and you really need somebody who's expert in the languages to, if you like, look again at the original documents with a modern view of the solar system in their head rather than a 19th century view, and to see whether they can separate descriptions of fireballs from bright aurora or from the Steve-like phenomenon. And you see all sorts, as you move towards the fringes, you see almost all sorts of, how can I put it, peculiar things described in the sky, probably describing something that actually happened, but very difficult to interpret.
Pioneer and Voyager was slingshot to the end of the solar system. What about the other way? Comet, or can they?
Yeah, a slingshot back to the Earth. Yeah, it can happen. Yes, Alexa's comet was one example in 1770, I think it was, and yes, exactly that process. Comets can in that case it was Jupiter doing the slinging, and the comet passed close to Jupiter. Alexa's comet was observed exceptionally close approach to the Earth, and for the first time in history it was recognized that not every comet was parabolic or near parabolic. Lexa was the example, but it then wasn't seen again. It was only subsequent to seen that on the way out it was hit the Earth. Well, it didn't hit. It passed close to Jupiter again and got booted into an even longer period orbit. So yet has not yet come back. So that's the kind of thing can happen. Yeah. So planetary cometary billiards. I think people sometimes talk like it. Yeah.
What was Q?
What was Q? Perihelion distance.
Perihelion distance.
That's the distance of closest approach to the Sun. So if this is the Sun, and this is the cometary orbit, then that's Q and that's big Q, that's small q perihelion, that's aphelion. And the orbit is very nearly rectilinear because it's a highly eccentric ellipse usually. Not the case of Encke, but of the case of most of the long period comets, because they go from a perihelion distance of 1 AU out to an aphelion distance of maybe 100,000 AU. So if you were to try and draw that, you'd be...
an ellipse, is it?
Yeah, it's on an ellipse, but it's an extremely long, thin one. Yeah. So you'd never be able to draw it except to see as two nearly parallel lines. Yeah, in some cases.
Well, thank you very much for it.
Well, thank you. And thank you again for inviting me. Okay.
Yeah.